So this next section is on QR factorization, and it's very much related to what we've done with orthonormal bases. We actually need orthonormal bases for QR factorization. So this is yet another way that we can factor matrices to make it more computationally quicker or easier in some kind of way. All right, so you'll see. So suppose we have a matrix A. So suppose A is an M by N matrix. So I think this is the first factorization method where we don't have to have a square matrix. So suppose A is an M by N matrix with linearly independent columns. Then we can write A equals QR. So this is our factorization, where so the first matrix Q is an M by N matrix whose columns form an orthonormal basis. Of the column space of A. All right, so the first part is if you find an orthonormal basis of the column spaces of A, that's going to be our Q. And then the matrix R, that's an N by N matrix. And it needs to be upper triangular. So an N by N matrix that is upper triangular. That means the stuff is on the top, zeros on the bottom. It also needs to be invertible. And its diagonal entries must be positive. All right, so this would be the result of our QR factorization here. All right, let's just jump right into an example. So we want to find the QR factorization of the matrix A, 1, 2, 0, 1, 2, 2. All right, so note these columns are from a previous problem we've done, but also note the columns are linearly independent, which we need for QR factorization. So the columns of our matrix A are linearly independent, and we want to find the QR factorization of this matrix. All right, remember, we previously applied Gram-Schmidt to this set of vectors, right? 1, 2, 0, and 1, 2, 2. Oops, these should be separate vectors. All right, so we applied the Gram-Schmidt process to these two vectors to get these two vectors, 1, 2, 0, 0, 0, 2. So check that video out if you missed that example. And this is an orthogonal basis. And then we took that orthogonal basis and normalized it. So then we normalized to get the orthonormal basis. Okay, and so our orthonormal basis consisted of the vector 1 over root 5, 2 over root 5, 0, and 0, 0, 1. So this is both orthogonal and normal. Okay, all right, so let's go back and figure out what we're trying to do here. Now that we've done all this back work, it says QR factorization, where Q is an n by n matrix whose column form an orthonormal basis of the column space of A. So we took the columns of A and we found an orthonormal basis. So these together is going to be our matrix Q. So we're going to let Q equal this matrix composed of these two columns. But now we have to figure out, well, what is R? Question mark. Okay, so let's do a little bit of proving and then we'll get to the answer. All right, so side work, QR factorization is how we can factor a matrix A. I am going to take the transpose of Q and left multiply on both sides. And normally, Q transpose and Q doesn't really mean much. However, in this case, it actually equals the identity, which never happens. It rarely happens. And I'll talk about why it works here. So it turns out, if we're looking for R, all we have to do is multiply Q transpose times our original A. But let's answer this weird question here. Why did this work when this usually does not work and give us the identity? So why does Q transpose Q equal I in this case? And the reason, or the answer to this question, is because the columns are orthonormal. All right, let's actually do it so you can see and believe me that it worked this time. So if you take Q, which we have up here, transpose it and multiply it by Q, just like what we have here. All right, so the transpose, where the first column will become the first row. Times Q. And when we do our matrix multiplication, we get 1, 0, 0, 1. Identity matrix. Interesting, right? So another question would be, well, could you have switched the order? So what about Q transpose? Does that equal I? Actually, no, it doesn't. Nope, it does not. So this is just a very strange situation. Okay, so normally I would end the video after 10 minutes, but we're almost at the end, so I'm just gonna push through for a couple more minutes. Okay, so now let's go ahead and find R. We know a formula for R right now. So that means that R is Q transpose times our original A. So here's our Q transpose. And our original A was 1, 2, 0, 1, 2, 2. So we're going to get a 2 by 2 matrix as our result. Looks like we're getting 5 over root 5, 5 over root 5, 0, 2. All right, we can stop here, but I'm going to make it look slightly better. This is just root 5. And note that this is an upper triangular matrix with positive entries down the diagonal. Okay. All right, do we believe that we have found the QR factorization? Let's verify this. Q times R. Here was our Q. Multiply it times our R. Okay, cross down, cross down. We should get a 3 by 2 matrix. So we got 1, 2, 0, 1, 2, 2. That's our A. We did it. We did QR factorization. So when would you ever use QR factorization? So actually, if you're using MATLAB, MATLAB does QR factorization. So note, this is the last note of our notes today. Okay, so if A is not n by n, MATLAB uses QR factorization. To solve the system AX equals B. Instead of what it usually does if it's a n by n matrix, LU factorization. All right, so that is the end of the section.